So what does a piece of code really mean? It sounds simple, but it's actually a super deep question. Let's dive in and see how we can actually formally define and prove what our programs are all about. I mean, think about it, right? We write some code, we hit compile, and we kind of cross our fingers and hope it does what we think it does. But when you're talking about critical systems, stuff for aerospace or finance or medicine, hope just doesn't cut it. We need to be absolutely certain. So the big question is, how can we pin down the meaning of a program so precisely that we can prove what it's going to do before we even run it? Well, it turns out there's a whole field of study dedicated to that exact question. It's called dynamic semantics. And look, this isn't just some abstract philosophical thing. It's a really rigorous science for describing what our code is doing while it's running. So let's unpack the 3 big ways people have figured out how to do this. Each one has a really cool analogy that makes it easier to grasp. All right, first up, we've got operational semantics. Now, the easiest way to get your head around this one is to think of a program's meaning as a recipe. Seriously, it's all about the step-by-step instructions. So here's the key idea. With this approach, the meaning of the code is the execution itself. That's it. To figure out what a program means, you just describe the exact sequence of changes it makes to the computer's state, one step at a time. It's super direct, really intuitive, just like following a recipe to bake a cake, right? The meaning is literally in the doing. And this is a perfect example of what I'm talking about. Take a totally standard for loop in C. What's its operational meaning? Well, it's not some high-level idea. It's literally its translation into a bunch of simpler steps that a machine can actually follow. Step 1, initialize with the first expression. Then step 2, check the condition in the second expression. If that's true, you run the body of the loop. Then you update with the third expression and you go right back to the start and do it all again. It's the perfect illustration of that recipe idea. The meaning of a for loop is just this exact sequence of simple actions. Okay, so that was the recipe. Now let's switch gears and look at our second approach, which gives us a totally different way to think about this. This is called axiomatic semantics. And here, the meaning isn't a recipe, it's a contract. So just like any real-world contract, this one has terms and conditions. In axiomatic semantics, those terms are just logical statements we call assertions. You've got the precondition, that's what you guarantee is true before a line of code even runs. And then you have the postcondition. That's what the code guarantees will be true after it's finished. And this is how they write it out formally. It might look a little weird, but you can just read it like this. If the precondition P is true, and then we run statement S, then we are guaranteed that the postcondition Q will be true when it's done. So the meaning of that statement S is basically its power to change any situation where P is true into a new situation where Q is true. Okay, let's make this real with an example. Say our contract says that after we run the line A equals B divided by 2 minus 1, the variable A has to be less than 10. That's our postcondition, our guarantee. So what's the absolute minimum requirement, they call it the weakest precondition, that we need for B to make this happen? Well, you can just work backward. If we plug the formula for A into our postcondition, we get B divided by 2 minus 1 less than 10. Do a tiny bit of algebra, add 1 to both sides, multiply by 2, and you find that B has to be less than 22. So there it is. B less than 22 is the precondition we need to guarantee our postcondition. The meaning of that line of code is that exact logical relationship. And that brings us to our final approach, denotational semantics. Now this one gets a little more abstract, a bit more high level. So here, meaning isn't a recipe, and it's not a contract. It's a translation. A translation into the pure, perfect, and totally unambiguous world of math. The whole idea here is to map every single piece of your programming language to a specific mathematical object, like a number, or a set, or a function. What's really different from the recipe approach we saw first is that we're not talking about coded steps anymore. Instead, we're describing how things change using these pure mathematical functions. So, let's say we start with something we all know, a simple function that just squares a number. Its denotational meaning is just, it's the direct translation into its math equivalent, the pure function f of x equals x times x. And the magic here is that if you do this for every single part of a programming language, you can then start to analyze and prove things about your programs using all the powerful tools of mathematics without ever having to worry about what kind of computer it's running on. Okay, so we've got recipes, contracts, and translations. I know this can all sound pretty academic, right? But the truth is, this stuff is the absolute bedrock of the reliable software we all use every single day. So let's talk about why this all matters so much. For starters, this is how we can prove with actual mathematical certainty that a program is correct. It's also absolutely essential for anyone writing a compiler. I mean, they need a perfectly clear definition of the language they're trying to translate. This stuff also guides how we design new, safer, more secure programming languages. And maybe most importantly, it's the engine that powers those formal verification tools that check supercritical software for bugs that could, have catastrophic results.
And all of this leads to a huge final question for today. We're moving into a world where AI is going to write more and more of our code. So, how are we going to formally define and verify what that code means? The challenge of understanding and proving what code does is about to get way more important. And you can bet that the very techniques we've just talked about are going to be absolutely essential if we want to make sure the code of the future isn't just powerful, but is also provably safe and correct.